Hey guys, so as promised, I am recording a free response practice for your Unit 3 exam that is coming up soon. All right. And so in this particular video, we're going to go over how to interpret this bright lines emission spectrum. Okay. And we have the emission spectra for different elements, and we're going to try to figure out what's in our unknown. We're also going to calculate our energy, all right? And we're going to do a conversion from nanometers to meters. Um, so that's something that I want you guys to be familiar with. And then we're going to use this model to talk about when electrons are moving from lower energy to higher energy and higher energy to lower energy and what is really happening, okay? All right, so let's take a look at this here. So it says below are diagrams of the bright line emission spectra for 6 elements in the spectrum of an unknown sample. It says based on this illustration, answer the following questions. Okay, so we have this bright line emission spectra, and we've talked about how these are basically like the fingerprints of elements in a sense. Each element has its own unique electron configuration, and so we know that that elements that are present that are excited to higher energies, these electrons that are in those atoms, they're going to go to those outer energy levels and then they're going to fall down. And when they do, they will emit electromagnetic radiation. And sometimes it's in the visible light spectrum. And so that's where we get all of these visible light emission spectra that we're looking at right now. So we can pretend that we're a scientist, we're on Earth, maybe we're looking at a distant planet, and we're using an instrument to analyze this light that's coming in. Okay, and we need to figure out like which elements are present on that distant planet and that are showing up in our unknown sample. And so we talked a little bit about how these elements are like fingerprints, or I'm sorry, the bright line emission spectra, okay, or spectrums of each of these individual elements are like fingerprints. And so we can kind of think about it like fingerprints, like we're getting fingerprinted. All right, Miss Ryholt was convicted of a crime. Not really, but well, let's pretend. And if I have been committed of a crime, no, that didn't make sense. If I have been accused of a crime, let's say, not committed of a crime, accused of a crime, and all of my fingerprints are not present at the crime scene, I'm probably off the hook. Okay. And it's kind of the same thing with these emission spectra. All right. If all of the emission spectra are not present in our unknown sample, then we know that that element cannot have been present in our unknown sample. And so the first thing you need to do when you're looking at these is you want to just try to eliminate elements that have lines at wavelengths that are not present in our specific sample. So this is our sample down here. Okay. So I'm kind of like, really with this one because there's so many, it almost makes sense to kind of work our way backward. All right. So I know that I have these two here, and these two are present right here. Okay, that's the only place that those are present. So I'm pretty sure that that one has to be present in my sample. Okay, all right, let's see what else we're working with here. Then we have this one. Okay, this is the only place, and that's consistent with what we just said. Let's look at another one. All right, we have this one. Okay, this one is present right here. Again, very consistent. Now, this one up here, like there's one right here that looks like maybe it could be, but it does not line up perfectly, and it has to line up perfectly to be in our unknown sample. All right, let's look at another one here. Let me get a different color. We'll go pink. All right, so we have these two here. And if I look up here, I see that I have these two here. Okay. And so I think sodium probably is part of our sample, but those are the only two lines on the sodium spectrum. And so all of sodium's fingerprints, quote unquote, are present in the sample. And so sodium we could say is in our sample. All right, we will keep going here. Let's do green again. All right, so I have green right here. And this one probably matches up, and maybe this one does too. All right, but I know that helium is not part of my bright line, or I'm sorry, it's not part of my unknown sample because all of helium's fingerprints, the lines on this emission spectrum, are not present. And so next I'm going to do this one. All right, and so this one's present. Again, that's not surprising. We would expect that to be the case. And this one is present there and pretty much nowhere else. Okay. So if I'm looking to see which one of these are present, the answer is cadmium is present and then sodium is present. Okay. So in this particular case, we'll write sodium is being present and cadmium. And in terms of which ones are not present, lithium is not present, helium is not present, and potassium is not present. And hydrogen is not present. All right, so that is pretty much it for that type of problem. All right, then it goes on to say, if a photon of bright light from the sodium spectrum has a wavelength of 589 nanometers, then what is the wavelength in meters? All right, so this is just a simple conversion it's asking us to do. And it's not surprising because we have to do this conversion quite often. Because usually, if we're going to be using something like wavelength, we're going to have it in a formula that uses the speed of light. And the speed of light unit is meters per second. When we use meters per second, we cannot use meters in a formula in one place and use nanometers in another place. It has to be the same. Okay, and so that's why we are going to go ahead and convert these. All right, so let's see here. Okay, so you guys know by now, I like to do this dimensional analysis style. It's not the easiest way, okay, but it does set us up for success later on in our chemistry course. So the first thing that we're going to do when we're converting is we're just going to write our known value, okay, write our given. And what we are given is 589 nanometers. The next thing we need to do is write our conversion factor. So I know that this is my conversion factor. Okay. My conversion factor could be written one of two ways. It could either be written 1 nanometer over 1 times 10 to the negative 9 meters. That's one way we could do it. The other way we could do it is if we're doing 1 times 10 to the negative 9 meters over 1 nanometer. Okay. So the way you know which one you need to use depends on what you start with. So if I am starting with the unit nanometers here, I have to have the unit nanometers down here because I'm converting to some other meter, which means I need to get rid of the nanometers. So I have to cancel them. So I'm going to cancel the nanometers. So I'm going to have nanometers down here, and that means meters is up here. It's the unit I want to end with. And that means that I have to go over here and pick the one that matches. All right. And so this one has nanometers on bottom. So let's use that one, 1 nanometer. And then on top here, I have my meters, which is just 1 times 10 to the negative 9 meters. So you could simplify it by saying that if you're going from nanometers to meters, you're going to want to multiply by this conversion factor. Whereas if you're going from meters to nanometers, you'll end up dividing. Okay. The more common scenario is that you're going to end up multiplying, but you just need to be aware of the why so that you don't get hung up and doing it the same way every time. And then if were to throw you kind of a curveball by asking you to convert from meters to nanometers, that you know what you're doing. Okay, so from a math perspective, we just need to enter this into our calculator because with dimensional analysis, we're just going to multiply these numbers on the top and divide by whatever we multiply on the bottom. However, we only have a 1 on the bottom, so we really don't need to do anything with that. So we're just going to multiply across the top. So let's do that. All right, so multiplying across the top, it's 589 times 1 second E, and then this -9. Do not use the minus sign. That's going to get you in trouble. And then this ends up being our converted number. Okay, 5.89 times 10 to the -7 to the -7 meters. Remember, in science, a number is just a number. Without the unit, it doesn't mean anything. All right, so we have to put the meters on there. Okay, so that is our number. And it makes sense too. If you remember earlier in the year, we were talking about metric conversions, and it's really just a matter of moving the decimal place the number of times that you need to convert between one and the other. And so that's why our answer here looks so similar to the answer that we started with. 589, now we're 5.89 times 10 to the -7. That makes perfect sense. All right. So now we're going to use the information from question 2 to calculate the energy of the wave that produces the bright yellow light from the sodium emission spectrum. Okay, so we need to calculate some things here. So it wants us to calculate the energy. So that means that energy has to be the unknown. Okay, and it's also giving us wavelength because we have wavelength up here. These are the only two things we know. I don't know anything about frequency, so I can't use my equation where we know that energy equals frequency times Planck's constant. That's not going to work. And then I can't use the one where it's speed of light equals wavelength times frequency because we don't have frequency. So I'm going to have to use my equation that kind of combines things and says that energy equals Planck's constant times the speed of light over wavelength. That's the one I'm going to use. All right, so we already know that H equals Planck's constant, which is always 6.63 times 10 to the -34 joules seconds. And then for the speed of light, we're going to simplify that to 3.0 times 10 to the 8 meters per second. That's good. And then the wavelength is the one that we calculated. We're going to take the number that we calculated in meters. Why? Because the speed of light is meters per second, and we're using it in this formula that we need to use. And so we absolutely must convert it to meters first, which we did. And so now I have wavelength, which is this lambda 5.89 times 10 to the -7 meters. All right, so now let's just plug this in our formula. So on the top, we have Planck's constant and the speed of light. So we have 6.63 times 10 to the -34 joules seconds times 3.0 times 10 to the 8th meters per second all over our wavelength, which is 5.89 times 10 to the -7 meters. Okay, now we just need to put it in our calculator. But before we do that, why don't we take a look at the units right here? So I'm taking it a little bit of a step further. Yes, you can just plug it into your calculator now, and that's fine. And you'll get the answer, and all is good. But if you take an extra second to really kind of just look at what's happening with the units, it's going to help you in the future. So we need to cancel out units until we end up with the unit that we should be getting for energy, which is just joules. And so meters per second, right here for our speed of light, you can kind of actually think of that as like meters and then over seconds over here, okay, times 1 second. If we look at it like that, we actually will cancel the seconds down here with the seconds in the joules per second unit up here. And we're going to cancel these meters here, meters, meters. And so the unit that we end up in is joules. All right. I take some extra time to really reinforce that because if I had realized how important the units were when I was in high school, um, I just would have gotten a much deeper understanding of how things work in these chemistry equations and all of the physics courses that I took. And so I just want to take a second to do that with you guys. All right, so let's go ahead and just put this in the calculator. 6.63 second EE negative 34 times 3.0 second EE8 divided by 5.89 second EE that negative 7. And so our answer is, whoopsie, here we go. Our answer is 3.38 times 10 to the negative 19 times 10 to the negative 19 joules. That's it. Okay, so we're almost finished. Now it says use the model below to answer the following questions. It says which electron transition creates light with the longest wavelength? Okay. The other one says which electron transition would have the highest energy and frequency? Okay, so the biggest thing to know here, and this is something that we've kind of been talking about um, when we've been discussing the practice packet. Okay, so let's see here. So I'm going to highlight the transition with the longest jump in energy levels. All right, so here I'm going from one. So I'm going one, two, three, four energy levels because I go from the principal energy level n equals one all the way to my principal energy level. Actually, this one here is n equals one down here. Okay. So I'm going from one to two to three to four to five. So that is one, two, three, four jumps. This one here goes one, two, three jumps. This one here is going to go one, two, three, four jumps. All right, so we basically have two electrons that have jumped from our first energy level all the way up to our fifth energy level. Okay, so we could actually say that these are the ones that have moved the farthest away from the nucleus. They've absorbed the most energy. All right, but our question doesn't actually ask like which one is absorbing the most energy. It's asking which one of these is creating the wavelength with the longest light, and which one is creating the highest energy and frequency. So we're not talking about the ones that are moving away from the nucleus, because the ones that are moving away from the nucleus, those are absorbing energy. It isn't until we're in a higher energy level and we're falling back down toward the nucleus that we release light and we release high energy, high frequency electromagnetic radiation. In that case, okay, let me just get a better color here. Let's do let's do this rainbow one. Why not? Okay. Let's just talk about the ones that we care about, the ones that are emitting electromagnetic radiation and sometimes light in the visible spectrum. All right, so we have one here. This one's going from outside to inside. Okay. And let's see, this one also is moving from outside to inside. And this one also is moving from outside to inside. The ones that are moving from outside to inside are producing light. And when I say light, it really could be any sort of electromagnetic radiation on that spectrum. The key thing to remember here is the more energy levels that you quote unquote fall from the outer higher energy levels, the higher the frequency and energy your light that you produce is going to be. So remember, we have this like light that's going to be emitting from these here because once these electrons absorb this energy, they have to fall from this higher energy to a lower energy because they want to be more stable. And when they do, they have to emit light, or they have to release that energy in some form. Okay, usually in the form of this electromagnetic radiation. And it's proportional to the number of energy levels where they're falling. Okay, so let's look at the first one here. All right, so this one here, it's falling one, two, three, four, five energy levels. All right, so we could say that A is going from N equals 6 principal energy level all the way to N equals 1. Okay, so that's a difference, which is like a delta of 5 energy levels. All right, next, let's look at E here. Okay, we could say that E starts at principal energy level 5, and it's going to drop to 4 and then 3. Okay, so N equals 3. Well, the delta, the difference between principal energy level 5 and 3 is 2. All right, so that one has not moved that much different. So let's look at F now. When I say that one has not fallen that far, is what I mean to say. Okay, now let's look at F. So F starts here at principal energy level 4, and it's moving to principal energy level 1. So that's a delta, a difference of 3. And so now we kind of understand A has fallen the longest distance, or the furthest distance. And then E has gone the shortest distance, and F is somewhere in the middle. Okay, so let's go back to the questions now. It says, which electron transition creates light with the longest wavelength? So if the energy is proportional to the amount of energy levels that an electron falls, that means that this one is going to have the highest energy. But we know that wavelength is has an inverse relationship with energy. And if that's the case, then the one with the highest energy would have the shortest wavelength. Okay. But that's not what it's asking. Let's see if I can spell shortest right. It's been a long day. Shortest. Okay. It's got the shortest wavelength. So, but we're looking for the longest wavelength. Okay, so we need to go all the way over here. So if E only fell 2 energy levels, that means it must have the lowest energy. And because we have this inverse relationship with wavelength, that means that we're going to have the longest wavelength. Okay, so the answer for this one is E. And the next question says, which electron transition would have the highest energy, highest frequency? So we already said that this one, the one that falls 5 energy levels, or a distance between energy level 6 and energy level 1, will have the highest energy. And we know that energy and frequency have a direct relationship. Okay, so the one with the highest energy must also have the one with the highest frequency. And so in that particular case, it's going to be number A, letter A. Okay. All right. So I think that that does it. If you guys have a good, strong grasp on all of these things, you're going to knock the FRQ out of the park and get that full 15 points on your exam. All right. Thanks.